What we have here is the Chapter 11 Test for Goodness of Fit stats class. And here we go as a sample problem here. It reads, an NBA fan wonders if the distribution of 4 NBA players' points per game was different between the 2014 and 2015 regular season. In 2014, Kevin Love scored 26.3% of the 4 players' points per game. James Harden scored 25.6% of the 4 players' points per game. LeBron James scored 27.3% of the 4 players' points per game. And Anthony Davis scored 20.9% of the 4 players' points per game. The 4 players scored a total of 93.5 points per game in 2015 regular season. Does the evidence suggest that the distribution of the players' points per game was different between the 2 seasons at the .05 level of significance? So first thing what we're going to do here is, because it's a lot of information, we're going to break it down into a hypothesis test. So our H0 is there is no difference between expected and observed points per game. And our null, of course, is there is a difference between expected and observed points per game. So what we're going to do first here is we're going to create some tables. We're going to separate it by year. 2014 over here and 2015 over here. So what we have here is 2014, Kevin Love, Harden, LeBron, and Davis. We have their points per game for that year. We have it totaled up here at 99.4. What we did here is we did the expected frequency. Now those are going to come out to these numbers here as we calculated. Now as we look at the 2015, we have the same setup. We have Love, Harden, LeBron, and Davis. We're going to have our observed counts in here: 16.4, 27.4, 25.3, 24.4, which is going to give us this nice round number of 93.5. Well, actually, I shouldn't say round because it's a decimal. Now what we have here is our expected counts formula, and that's going to be this total multiplied by this percentage, and that is in fact going to give us our expected counts totals. Let us also remember that our degrees of freedom is known as n minus 1, and in this case it's going to be 4 minus 1, which of course is going to give us the degrees of freedom of 3. Now if you're using the calculator, which isn't recommended for this particular problem purely because this is a 0.5 and not a whole number, therefore when you enter it in you're going to get some sort of domain error. But if you are using the calculator, it's important to remember that we're going to use list 1 as our observed counts and list 2 is our expected counts. Of course that will be in the stat list editor. So to find the test value, we are going to use the chi-squared formula. And if you do it all here by hand and paper, it'll come out to a 4.479 as a test value. Okay, these can all be found in the notes and everything that Ms. K gave us, as well as many other textbooks. So this is going to give us a test value of 4.479. Now, of course, in order to fully run this, we're going to also need the critical value. To find the critical value, given that you have all this information entered correctly in your list 1 and list 2, you're going to go to inverse, chi-square. Area is going to be 0.95 because we have that 0.05 level of significance up here. Your degrees of freedom is going to be 3. And when it's all said and done, your critical value is going to equal 7.815. Remember, you're only going to have one critical value because it's always a right tail test. With that being said, it's now time to plot on this graph where we stand. So first we're gonna cut this off. We're going to mark that this is 0.05, given by our 0.05 level of significance, which means that the area to the left of it is going to be 0.95. Our critical value could be plotted right here at 7.815, as found right here. Our test value, as we found up here, is going to be 4.479. As you can see, this test value lies way on this side and outside of this shaded or critical region. Therefore, from this hypothesis test tells us to do not reject Do not reject this. Our reason being for that is because there is not sufficient evidence to claim that there is a significant difference between expected and observed points per game. With that being said, so in other words, this question, the answer is no, because we're not rejecting, and we're saying that there's not evidence to claim that there is a difference between these different points per game. Reasons being for this could be, well, if you look at 2014, 2015, many of these players have switched teams and are playing together, so the points per game is going to be different than how it was, a year or two ago. Basically, there's multiple variables, but that gets into whole dependent, independent, all that good stuff. But the main thing to know here is do not reject, and that's chapter 11 in a nutshell.